My name's Sebastian. I would like to talk about temporal model merging. So before we dive into the temporal part, let's talk about model merging. So with some exceptions, most of the model merging literature assumes that we have a base model that is independently trained on a bunch of tasks, and then all those model experts are merged simultaneously. However, in practice, those tasks can emerge over time. So in this work, we ask the question, what is the best strategy of temporal model merging? And in order to answer that question, we introduce this framework we call temporal integration of model expertise, or TIME for short. And we highlight three different axes that we analyze. So three different design choices that span the design space of temporal model merging. The first one is initialization, then it's deployment, and the choice of merge technique. So in the temporal setting, we assume that at each task we have a bunch of data that we train the model on, and then we store all the past experts from the previous tasks. And because we have those experts, we are able to perform a merge of all the past experts. So we have a choice of either initializing with the base model, with the last trained experts, or with all the past experts. And the last choice we have is the exponential moving average. So this means that we just maintain a single additional set of weights, and we always merge the last expert into that rolling average. Then we have the choice of the deployment merge. So this is what happens after the training. And here again, we can either use the last experts, we can merge all the past experts, or we can use an exponential moving average. And finally, we have the choice of the merging technique. So this is what most of the multitask merging literature innovates on. And here we have a bunch of methods to choose from. So initialization is what happens before model training. Deployment is what happens after model training on a specific task. And the merge technique just tells us how to reconcile the parameters of individual experts to combine them into a single model. So before I show any results, I would like to talk about the dataset that we use. And it's called FOMO in Flux, Foundational Model in Flux. It's a dataset or rather a benchmark we introduced in a previous paper. And the idea here is that we take a bunch of existing computer vision datasets, typically classification and retrieval datasets, which come with some labels. And for each image in that benchmark, we synthetically generate a caption and then merge that caption with the label to produce a caption that is grounded in this class information that we get from the dataset. And all this covers a bunch of domains, such as satellite images, paintings, sketches, images of textures, medical images, datasets like MNIST, synthetic datasets, and so on. So it's a broad variety of visual domains. And then at each task, we introduce new concepts from this benchmark. And there's two types of datasets in that benchmark. We have the held-out evaluation datasets, which we never train on, and these are used to measure the foundational capabilities of the model, so sort of the zero-shot retention capabilities. And then we have the adaptation datasets, which are actually used for training. So whenever you see knowledge accumulation on the plot, it means how well we're doing on the adaptation datasets. So these are the datasets we train on, and we measure accuracy or retrieval performance. And whenever you see zero-shot retention, that's the performance on the held-out datasets that we never trained on. And this is to measure to what extent we're losing this foundational property of the model. So here you see sort of the first two axes of the time framework, and that's the choice of the initialization merge. So how do we merge the past experts before we train? And the deployment merge, so how do we merge them after we train? So for example, FT-all means we always start with the last expert before training, and we always deploy a merge of all past experts before evaluation. The gray star is the zero-shot performance, so that's where all the models start, and the orange star is the multitask performance. So this is training jointly on all the task data. So there's two things I would like to highlight here. First of all is that those choices matter, so the curves are very different. The choice of initialization and deployment is important. And the second thing I would like to highlight is that there is one choice that consistently performs the best across model scales, across the number of tasks, across data orderings, and that's the choice of an exponential moving average initialization and exponential moving average deployment. And there's a neat thing about it because it's an exponential moving average, we don't really need to store all the past experts, we can just have a rolling average. So in terms of memory, it's also a much more attractive method, and it so happens that it's also the best performing one. Now, I've covered the first two axes, and let's now move to the third one, which is the choice of a merging technique. And what we find is that in the temporal setting, that doesn't matter as much. So all of these are here applied on top of the exponential moving average initialization and deployment. And it turns out that even though in the multitask settings, those techniques perform very differently, in the temporal setting, the gains from using a better merging technique are marginal compared to the gains you get from getting the right initialization and deployment. And the last thing I would like to show is the scaling behavior in terms of both model size and compute. And again, the solid star is the zero-shot performance. The outline star is the multitask, so trained jointly on all the tasks. And then each curve traces a trajectory in this knowledge accumulation, zero-shot retention space. So you can see that for the smaller models, even the multitask baseline, even though it improves on accumulation, it sacrifices a bit of this zero-shot retention. And you can see that every curve, obviously it goes up, so as the training progresses, we gain knowledge accumulation. But the simple replay, so continual fine-tuning with replay, suffers a lot in terms of zero-shot retention. So for smaller models, it ends up being much worse than the multitask. However, model merging, even for smaller models, offer a much better trade-off between zero-shot retention and knowledge accumulation. And as the model scales up, it even closes the gap to the continual fine-tuning with replay in terms of knowledge accumulation. So not only it offers excellent zero-shot retention, in fact better than the multitask upper bound, it also closes the gap to replay in terms of knowledge accumulation. And another remarkable result is the scaling in terms of compute budget. And here on the right, we see that the best-in-time, so model merging with exponential moving average initialization and deployment, is able to not only match the multitask upper bound, but even exceed it at higher computational budgets. So to sum up, our contributions are we introduced and formalized the setting of temporal model merging and describe the structured framework. We show limitations of existing methods. I haven't shown that in this presentation, but you can have a look at the paper. We performed a systematic exploration of initialization, deployment, and merging techniques, and we propose a technique that works optimally balances knowledge accumulation and retention, and is able to surpass joint training with compute scale. And with that, thank you very much, and you can have a look at the paper here.
Do you have a sense if the results would vary with the number of tasks?
Yeah, so we look into that. The best in time is still the best, which is encouraging. Yeah, model merging, like it works surprisingly well, even over like 20. So these results are for 20 tasks, but we look into 50, 100, and still offers a good trade-off. Yeah.
I have a question, maybe. So you show that as you increase the number of flops, your best-in-time method is closing the gap with the multitask.
Yeah.
Oracle in some way. Why? With more flops, is like just more flops, like more training or bigger model?
Yeah.
And do you think that gap will be ever completely closed and you will be even better than this baseline?
So I think what I showed is the average of zero-shot retention and knowledge accumulation. As you increase the computational budget, the multitask baseline it really loses the zero-shot retention. So that's where the closing of the gap is coming from mostly. This is the largest budget we were able to run on our compute, but yeah, it would be interesting to see what happens even further up.
And how this budget is distributed? Is it due to a bigger model or simply like a smaller model but much more training steps?
It's the same model. So model scaling is on the left. Here it's a bigger model, but on the right we fix the model to be 16, I think, and then we just train for longer. Yeah.
A question. With the EMA initialization and deployment approach, was there anything systematic you observed in terms of like the parameters for the EMA weighting, in terms of like how that changes with the number of tasks you're dealing with over time?
Yeah, so we just used a single weight across, and we found that just 0.5 works the best. So yeah, not as exciting. But